Okay, good morning or afternoon. Again, we are here today for the real gas behaviors lecture. Specifically, in order to accomplish the lab goal, we're studying what's called the van der Waals equation. So real gases, we've been studying ideal gases in chapter 5, but real gases deviate from the ideal behavior described by the ideal gas law. So real gases deviate from, quote, ideal behavior. Okay, under two conditions. These two conditions are when the temperature is very low and or when the pressure is very high. So aside from these two sort of unique scenarios, gases behave according to the ideal gas law, where PV equals nRT. But when you get really, really cold, we're talking just a couple of degrees Kelvin, or to really high pressures, and that varies from one gas to another, what it considers to be high, we start to see some abnormalities developing in the behavior of a gas. And so there's two specific things that happen. All right. One is that the volume is affected. Okay. And the second is that the pressure of the gas is affected. Okay. The volume is going to become affected. We can think about what life is like as a very high pressure gas. At very high pressures, you have a lot of gas particles crammed into a small space, is one way to cause that condition. All right. And at that scenario, imagine the walls of our room shrinking down and getting smaller and smaller. There's so much freedom between all of us right now. But as the room got tighter and tighter, right, we would get closer and closer together. And that postulate from the kinetic molecular theory that says that gases have a lot of space between their particles, that goes away. All right. And in that instance, the volume that we occupy, or the volume that the gas particles then occupy, becomes a significant value, not something we can ignore anymore. All right. And so we have a correction, a corrective factor, all right, that would say that the volume totally occupied by the gas is actually a little bit bigger than the ideal volume would predict because of the gas particles themselves. Right? You can sort of imagine them bulging out like the container a little bit because of their volume. All right? So the volume is actually increased due to the particles. Okay? So in ideal gas behavior, right, going from PV equals nRT, the ideal volume of a gas would be nRT divided by the P, the pressure. But the real volume will be the nRT divided by P plus N moles times B. So B is a corrective factor. Okay. So B accounts for basically how big the particles are, depending on what gas you might be working with. It's a really small value for monatomic gases like helium, all right, or argon. But as you get to larger, more complex gas molecules, in lab today we're working with sulfur hexafluoride. A molecule of sulfur hexafluoride will dwarf a helium molecule. And so it, of course, takes up a lot more space, each one of those molecules. All right? Now there are several different versions of attempting to model real gas behavior. This version is what is called the van der Waals equation. All right. There have been several. This was one of the earliest ones that successfully predicted real gas behavior, but the more sophisticated models have been developed since. But just to give us an idea of what's going on with real gases, I want to talk about the van der Waals equation. Okay? Now, pressure. The pressure of the gas would also be affected. One of our other assumptions in the kinetic molecular theory is that the particles have essentially no interest in each other. Two gas molecules just zoom by each other, right? Or if they do hit each other, we called it an elastic collision. They're just like two pool balls, bounce off each other, and they're gone. But at these conditions of high pressure or at very low temperature we now know means less energy. Less kinetic energy means the molecules are moving slower, so they're not behaving like these hard billiard balls that we've imagined on a pool table. They now start to behave more like softer, squishy materials, and when two molecules collide, they kind of stick for a second. All right? And when two molecules pass each other, instead of just zooming by, it's kind of like they kind of are slowed down, like to look at the other molecule is one way of imagining what's happening here. All right? Whereas if they had a lot of space, they wouldn't be able to see each other or pay attention. But when you cram them in, like if you were in a crowd, right? You can't walk the day after Thanksgiving if you go shopping, right? You can't walk in a straight line to the object that you're interested in. You have to weave your way through a crowd of people, and that's going to take longer. The effect that this has in a gas on its pressure is the net result is to decrease how often the particles get to collide with the walls of the container, because they're colliding with each other a lot more. And they're sort of sticking temporarily to each other. And they've got to get through the crowd in order to get to the walls. So the effect here is that the pressure is decreased due to sort of the, if you want to think of it as the congestion. Okay? But it's most strongly due to what's called the intermolecular forces. Something we're going to study in chapter 11, so I can't go into it in too much detail right now. But that's the idea that when two particles pass each other, they kind of slow down to see if they are attracted to each other. And do they want to stick to each other? All right? That's what the intermolecular force would be. Okay? So in the ideal gas law, our pressure would be nRT divided by V. In the van der Waals equation of state, it's nRT divided by V, and again with a corrective factor. We're subtracting A times N over V squared. And so A is a... Alright, so as I was saying when the video cut off, A is a second corrective factor. And together, A and B are known as the van der Waals constants. Of a gas. So our text and other resources would provide a listing of these two values, A and B. The goal of today's lab will be to experimentally determine A and B for a real gas. And so that's what we're after with the exercise that we're doing today. The way we determine them is by measuring something in the lab. Now B is essentially the volume of a single molecule or atom of a gas. So not something that we're practically going to measure, right? And A is related to the, if we look at what it's attached to here, it would be the pressure associated with a single molecule somehow of an atom. Again, so we're not really going to directly be able to measure these. And we need to come up with derive some experimental properties or values that we can more easily measure in the laboratory and associate to these two values, A and B. All right? And that's what the bulk of this exercise that I'm in right now will be, showing you how these constants rely on a couple of experimental values that we can measure. The good news is you'll never have to do this derivation again after I do it for you. All right? The rough news is it's a little bit painful to sit through, but it's an awesome exercise to experience, I think, so that you understand why there's so much math incorporated in your chemistry curriculum right now as well. Okay, so that's a big part of what we're getting into today. Okay, so first, before we go too much further and get into the A and B, if we look at these two equations right here, all right, they both still contain this nRT factor that we would have. So if we were to solve each of those equations that we had, solve the real, quote, V and P for the nRT term, okay, we can combine them, since they're equal to each other, and we would come up with what we call the van der Waals equation. Okay? So while this is, each of these respectively is the van der Waals equation for the pressure or the volume, neither of these is analogous to the ideal gas law up here, where pressure and volume are multiplied by one another to equal nRT. All right? So essentially that's what I'm trying to get to, is this form, but for a real gas. And here's what it would look like. The pressure would now have the A divided by NV squared added to it. So we can see that this would come over to here. All right? And then it would get multiplied by the V. And then the volume would then have the NB subtracted from it. So then that's what would equal nRT. Okay? So this becomes the van der Waals equation. All right? Okay. In order to do the derivation that we're working on today, it would be helpful if I redefine one of our variables, which is, or actually two. If I combine two of the variables together into what's called the molar volume. The molar volume, Vm, is simply the volume divided by N. So we see right here we've got N divided by V. That's just going to be the inverse of molar volume. All right, and it's a little bit more helpful if we can always express volume in relation to how many moles of gas we have. Because we know if we had more gas, more moles, we would have more volume. But the ratio would not change, all right, no matter how much gas we have. So it's a little easier to think about it in terms of that ratio, and then we don't have to have as many n's popping up in this equation. So the van der Waals equation, when I use that substitution, becomes P plus A over molar volume squared equals, molar volume minus B. And that equals just RT when I've divided through by N. So I've also made this substitution and divided by N on both sides of the equation. That's how this V became this Vm. Okay? And this version of the van der Waals equation is where I'm going to get started with the derivation. All right. The key to solving for these A and B's lies in understanding a little bit of behavior that we haven't seen yet. So I'll just have to tell you about it. Okay? But when people were studying these gases, what we came to understand was that for each unique gas, there's something called the critical temperature. Again, when we get into chapter 11 and we study all phases, then this will become a little more commonplace to us. But the critical temperature is the temperature above which we can no longer distinguish between the gas and liquid phase. Okay, you lose the ability to distinguish between the gas and liquid phase because, if you want to know what's happening, it's because the density of the liquid has decreased to become gas-like. Right? Everything, pretty much, its density decreases as you raise its temperature because it expands. The mass stays constant, but the volume expands, therefore the density is decreasing. And a liquid is essentially getting heated up so much and it's stretching out that it assumes a density that is the same as that of a gas. All right? Is there a question? Yeah.
Dr. Steele, so you're saying even at a very high temperature or very high pressure, when the temperature gets to a certain point, then it's no longer indistinguishable?
Mm-hmm. There is also a critical pressure at which this same thing happens from the gas side, because the gas, you're compressing it and its density is increasing and it becomes liquid-like, but it hasn't gone through a phase transition. All right. So these are called the critical values. When we cross over this line where it becomes difficult to distinguish between these phases. All right. Not every substance has one, as it turns out, or has one that we can measure in a safe setting. But many substances we're learning do have these critical temperatures and critical pressures. Okay. Now, what's important is that as we approach this critical temperature, okay, the change in the pressure of our real gas starts to stop changing. All right. So as the temperature is changing, we know that from our study of gas laws, the pressure, temperature, and volume are all kind of coupled together. All right. So, but as the temperature is changing, the pressure would also be changing. As you approach this critical temperature, the pressure stops changing. All right. Now, just hearing it that way might not sound too bad, but what that means, okay, for us, so the pressure stops changing as we approach and reach the critical temperature, T subscript C. Okay? So critical temperature, T subscript C, this is what that means. In mathematical lingo, which we need to do, what's, for those of you who've had calculus, what's an expression that we often invoke when we're talking about the change in one variable with respect to another? Derivatives, right? All right. Somebody said derivatives. The derivative of one thing with respect to another. All right. And so if you haven't had calculus yet, I'm sorry that this might get a little bit above your head for the next 15 minutes or so. All right. Actually, the next 5. All right. But that's just the nature of the beast. We can't do certain things in chemistry without understanding certain facets of mathematics, like calculus, differentiation, and integration. Okay? So a derivative really is nothing more than a slope, delta y over delta x, where the delta x gets really, really tiny. And you start to look at a really tiny change in one variable. And so you're talking about instantaneous change of the other variable is the language that we often associate with it. Okay? So the pressure is changing with respect to this molar volume. So what we want to calculate, what we would say in calculus language, is that the partial derivative of pressure with respect to volume. English, how pressure is changing as volume changes, okay, at constant temperature is equal to 0. That's what's really important, is that you understand that's what I'm saying. All right, this sentence up here. How the pressure of this gas changes is now not changing, all right, at this critical temperature. All right. To come up with this expression then, the derivative, the first derivative of this expression would be, okay, when you take the derivative, for those of you who have done it, if you had an expression like x cubed, the derivative of x cubed with respect to x would be 3x squared. The 3 comes down, we say, as the coefficient, and then the power is decreased by 1. So essentially I need to do that, where P takes the place, of the pressure here with respect to what's going on here. Okay? I'm going to just give you these derivatives. Okay? You can ask your calculus teachers to verify this when you get to there. All right? So the derivative equals negative R critical temperature now. So I've essentially got RT here, divided by molar volume minus B squared plus 2A over molar volume cubed. Okay? So you can kind of maybe start to figure out, if this is new stuff to you, where these pieces are coming from. Here's a Vm minus B that was associated with that guy right there. Here's a Vm cubed, which is associated with that Vm squared and the A that we had there. Okay, that's where these pieces are coming from. All right. Now, what's also true, if you've had some physics or your calculus, right, the classic ways to introduce differentiation are position in physics. How an object's position is changing over time. That's velocity. That's speed. So if you had an equation that told you where a ball is, a ball that's rolling, okay? If you had an equation that told you where that ball is, x, its position, at every time t, the first derivative of that equation is the speed of that ball at each of those times, okay? And then the second derivative, if you take another derivative, is the acceleration, right? Because you could, if you're in a car, you can put your foot on the gas and your position changes, but your speed is also changing. You know, you're going from 0 to 10 to 20. So your speed might not be constant. That's when you have acceleration, okay? So it's kind of odd to think, but what's also true at the critical temperature is that the second derivative of P with respect to Vm is also 0. So how the change is changing is 0. So really, everything is stopped at this critical temperature, in other words. So what we want to do is take the second derivative, delta squared pressure dVm squared, at the critical temperature. This is equal to 0. So then the derivative of this expression that we started with or developed up here would be now 2 RTC over Vm minus B cubed minus 6A over Vm to the 4th. All right. Now, how is this going to help us? Again, our goal is to get A and B, which are in both of these expressions. All right. What I'm trying to do are develop some equations that have A and B that I can link to one another, substitute one in for another, or solve for one variable to substitute for another. That's called solving simultaneous equations. All right. It's a common algebra process. At this point, the calculus is done. All right. For those of you who are kind of worried, we're done. All we needed the calculus for was to get these two derivatives. All right. What's important now is that both of these equal 0. So if they both equal 0, we could set the two equations equal to each other, right? And then we'll start to get some simplification occurring, all right? Or we could also see that they both contain RTC. So that's actually how I'm going to proceed. We've got a bunch of different options. We could say they both have VM, or we could find out how they both relate to VM. The way I'm going to proceed is to solve both of these for the RTC term, and then set equal to each other. So RTC, so I'm going to go on the left and the right. From the first derivative, RTC would be 2a over Vm cubed times Vm minus b squared. From the second derivative, RTC would be 3a over Vm to the fourth times Vm minus b cubed. There's a lot of commonality or common terms between these two equations, I hope you can see. All right? So you can start to cancel a bunch of stuff out. What's something that someone sees that we could cancel out from the left and the right side of this equation right now? Jimmy?
Vm minus b squared on both sides.
Okay, I've got a Vm minus b squared. It's not Vm minus b squared over here, it's cubed, but I can take away two of them. So I am going to be left with 1 Vm minus b on that side. Good. What's something else that cancels out? Again, we're ignoring RT in the middle now.
You take it out Vm to the cube on both sides. And that would get rid of it. You have one left on that side.
That's right. I'll have 1 in the denominator, unit of Vm left. One more thing. I could take out the A. Yeah, the A can cancel out on each side. All right. So this simplifies itself pretty well. I'm left with, after that simplification, 2. Sorry. I'm actually left with 2 equals 3 over Vm times Vm minus b. So this becomes 2 Vm equals 3 Vm minus b, or b equals that's 3b. 3b equals Vm. Wasn't one of my goals to try to find out how to relate these van der Waals constants to something I could measure? So if I could measure the molar volume of the gas, that would give me the B value right there. Okay? Unfortunately, it's not the easiest thing to measure. All right? Measuring molar volume is much more difficult than measuring pressure and temperature values. Obviously, temperatures come to us pretty easily from, a thermometer, and pressures from a pressure gauge that we can stick into our experiment. Molar volume would rely on measuring volume, which isn't that hard, but more difficult knowing exactly how many moles of a gas are present in a sample. And those are usually tied to the pressure and the temperature, so it's the most difficult of the three. So what we're going to do is we're going to use this sort of as a placeholder and continue to see if we can't get A and B in terms of the pressure and the temperature of the gas. All right. All right. And so the first step would then be to use one of the equations that we had earlier. All right. I'm going to go back to the first derivative. The first derivative expression was negative RTC over Vm minus B squared plus 2a over Vm cubed equaled 0. I can now substitute that Vm equals 3b. And so I'll substitute that here, and my equation becomes negative RTC over, this would be 3b minus b, so 2b, right, which would be squared then, plus 2a over 3b, which is cubed. That's going to equal 0. All right, I can sort of put one of these terms on the other side. So I'll have RTC over 4 times b squared. I've made this positive, so technically I've moved it to the right side. But that equals 2a over 27 times b cubed. Now, this isn't getting me a whole lot, closer to my answer right now. What I'm going to do is say, okay, then I'm going to solve for the critical temperature, because critical temperature shows up in a couple of different places. So the critical temperature in terms of these variables would end up being 8a divided by 27 r and b. Okay? So this expresses this critical temperature, this temperature when we lose the ability to distinguish between gas and liquid, in terms of, the van der Waals constants, actually. All right, so actually kind of opposite of what we want. We want A in terms of T and P if we can, or B in terms of T and P. But we've got T in terms of A and B. And then R is the same thing you're used to it being, the ideal gas constant, the universal gas constant. Okay? So now we can substitute this TC somewhere else to try to get rid of T and C and replace it with an A and a B, actually, that are closer to what we're getting at. And we can still continue to use what I just erased, that anywhere that molar volume shows up, it's 3B now as well. So we're sort of building up these substitutants that we can use, okay? These things that we can substitute. All right? So let's go to the van der Waals pressure equation. Way back earlier, the van der Waals equation for pressure was R at Tc over Vm minus B minus A over Vm squared. So now I'm going to be substituting for molar volume and critical temperature. This gets a little bit hairy. R 8A over 2B 27 RB minus A over 3B squared. I had two substitutions here. That's why you see 2B and then a B over there. Okay. And then as I start to simplify, this first part becomes 8A over 54B squared minus A over 9B squared. Aha! We've got similar values for exponents there, B squared. So we can combine these two fractions if we give them the same denominator, right? 54, 9 will scale up to 54, right? If I multiply this by 6, so this is kind of like 6A over 54B squared. So I could then add those two. That would give me 2 A's left in the numerator. 2 divided by 27 would give me A over 27B squared. Okay? Now this would become the critical pressure because we defined it at the critical temperature actually as well. All right? So right now we've got critical pressure in terms of A and B. We had earlier critical temperature, I still have it, in terms of A and B. And we have molar volume in terms of B. So we got our three sort of values relating to the properties of a gas defined in terms of A and B. All right? Thinking of an experiment now where we can observe these conditions would allow us to solve for A and B. But as I said, it's hard to find molar volume. But we can find the critical temperature and critical pressure of a gas. This is something we can watch, all right? And we have a device in the lab here that I'm going to show you. It's located, can't see it on the camera, but it's located back here by this first hood. And we'll operate that in a little bit, where we can measure the critical temperature and critical pressure of a gas. We'll physically see the gas change into a liquid, and then we'll actually see it disappear. Like we lose the ability to see the difference between gas and liquid in the same chamber. Okay? And so that's where we'll be at. Okay? So in order to get A and B, got just a little more algebra to do, where we're going to have to do some substitution of these values into one another. So working with the critical pressure, from the critical pressure being 2A over 27B squared, we can temporarily say, all right, well, A would equal then 27 times the critical pressure and B squared. I can substitute that then into my critical temperature expression, 8A over 27 RB. So I'm going to use this A down here. This is going to eliminate A. And it's going to give me T in relation to B only now. Or B in relation to T and P. Okay? So this becomes 8, if you want to see the substitution, times 27 PB squared over your 27 RB. And we're going to get a lot of simplification. Our 27s are going to cancel. All right? One of our B's is going to cancel as well. All right? And we end up with 8B times the critical pressure over R. It doesn't matter if I write B and then PC or PC then B. You know, it's all multiplication, so it doesn't matter. Okay? So this is equal to TC, keeping that from the left side. So B, the van der Waals constant that we're interested in, equals R TC divided by 8 PC. We now have, if we can measure the critical temperature and critical pressure, we have B, the van der Waals constant then. Okay? So this is one of our final end results that we're after. Okay, sorry the video cut off again. We had just derived that B can be found from the critical temperature and critical pressure of a gas, which we can measure directly in the lab with the device that I will show you, or the lab instructor will show you. Okay? Now all that's left is to take B and substitute it back into our equation for A. So A equals 27 critical pressure times this R TC over 8 PC, whole thing squared. And so this simplifies to, it doesn't look very simplified, but 27 times the critical temperature squared times R squared divided by 64 and the critical pressure. Just one unit of that, since you get one cancellation of the critical pressure. And so again, what we're getting here at the end is A defined in terms of two measurable properties of our gas, critical temperature and critical pressure. All right? So it took a little while to get through this derivation and to understand, but we now are able to, for any gas, if we can measure accurately its critical temperature and pressure, we can understand how significant its behavior deviates from ideal behavior at extreme conditions. Now this relates to some other stuff that you'll have in your homework and in lab. In homework more. You can use, because there's a table in your book of A and B values actually just given to you, you can use them to calculate what is the real pressure of a gas, what is the real volume of a gas, and see how significant it deviates from the ideal pressure that's predicted at a certain temperature or certain pressure. All right, and that's part of the lab exercise that we will do today as well. So, Lindsay, if you wanted to bring up the projector over here, I'll actually walk you through real quick. This is getting us a little bit ahead, but in the interest of having it all condensed, the on button. We are very shortly going to measure the critical temperature and pressure of sulfur hexafluoride. That will take us all of 5 minutes to do. All right, so the lab experiment's very short, if it even takes that long. What we're more interested, though, is in using the critical temperature and pressure to do some other calculations. All right, I have to get typed in here. I'm typing at an angle, I can't type. All right, so in your data analysis template for this experiment, after we've done the basic stuff of calculating our A and B value for sulfur hexafluoride, I have some extension exercises thrown in there to make you actually do something for the lab. Okay, what you're going to have to do is for sulfur hexafluoride. Okay, we're going to complete this table that we have, and this is in your data analysis, but I've made it real quickly in Excel. So for a given list of pressures, and assuming these are the ideal pressures, 1 atmosphere, and then jumping up to big pressures, 100, 200. So these are enormous pressures. This is when we're going to start to see deviations of a real gas, or a gas from its ideal behavior. Okay? First thing I want you to do is, for a single mole, to calculate the volume of that gas. So, we know, ideally, PV equals nRT, right? So the ideal volume is nRT divided by P. You're going to use 1 mole, all right? And you're using 273 Kelvin. So this becomes a matter of, in this cell up here, typing the equation equals, you don't need to worry about the 1 for N, but you would type in your ideal gas constant, 0.8206 atmosphere liters per mole Kelvin, times the temperature, 273, and then divided by the pressure, so that is A2. You could just type in A2, or you could calculate A2. Right? Now you can see I've got you doing enough calculations. You're going to want to do this in the spreadsheet and not by hand, because it's just going to be a lot of buttons to push. So then when you hit enter, you can then, let me see your, it wants a time symbol between the two numbers that you put there, Lindsay. You got it? Okay. And this is, that makes sense. This is we know that 1 mole of gas at standard temperature has a volume of 22.4 liters. So now Lindsay can just grab the little corner of this and fill it down, and bang, we have all of our volumes predicted. Okay? Real quickly, does this match what we think about for gases? As the pressure increased, look at what happened to the gas volume. It is decreasing, if you could see that. Okay? Now, in the next column over here, you are directed to take the ratio of pressure times volume divided by R and T. So this would be equals A2, your pressure, times B2, volume, divided by, all right, 0.08206. You can put this in parentheses, I guess, times 273. Now, what's this really? That should really just be N, how many moles of gas you have. So this whole column should equal 1. It won't be much interest, but this is setting the stage for something we do later on. Okay? There we go. And then go ahead and fill that column down as well. Okay, 1, 1, 1, 1. Not very exciting, right? Okay. Now, that's the ideal behavior. So now we're going to shift over to real behavior. So the real pressure from the van der Waals equation that we have in our report is nRT over V minus A N over V squared. So we need to figure out how to type this equation in to Excel. All right. What we're going to do here is we can assume, by the way, ideal behavior for the volume when we're doing this. Okay. So again, this equation would be equals, the N is still 1 mole, that's fine, 0.08206 times our temperature, 273. That probably needs to be in parentheses, divided by B2 minus then, all right, we need our A value for sulfur hexafluoride. Okay, so I can look it up here real quickly. Actually, I can't look it up. It's not in the textbook that I'm looking at right there. Okay, so let me get an average. Let me pick one from a different gas. It is in your textbook. It's not in this different textbook that I'm looking at here. 2.25 is listed for one other gas, but this is not actually SF6. Sorry. But that's what you'll do. You'll put the A value that you have right there. And then you would multiply this by, parentheses, 1 divided by, the ideal volume was over in B2 again, end parentheses, caret 2. That's how you do squared in an Excel. Okay? And that should give you the real pressure. Now, it's been a while. I've put a lot in your brain. But remember that the real pressure of a gas, we said, is always less than the ideal pressure because of the stickiness of the particles. So as we fill this column down now, we want to compare it to what we had over here. All right, oh, that's way, way less. Holy cow. So let me see if we've got it right.
You wanted the critical pressure for SF6?
What was that, James? Sorry?
You wanted the critical pressure for sulfur hexafluoride?
No, I wanted the van der Waals constant for A is what I was after there. Okay. That's all. All right. Well, this might be okay. Actually, what this tells us is that we're above the critical pressure, actually, and I think that's why this goes negative. Can you get back on your formula here? What is it? This is okay. That we don't need another. That's okay. I think this formula is okay. And if I'm remembering from doing this in years past, where this value turns negative is going to change from one gas to another because of the number that you put in down here. Okay, so don't be alarmed by this for right now. Okay. Now, let's repeat this. Let's find the real volume. Our real volume had the nRT over pressure plus N times B. So our equation here in E would be to type in equals, again we don't need the 1 for the mole, but 0.08206 times 273 divided by the ideal pressure we can use, pressure ideal, so divided by A2, all right, plus then, again we don't need the moles, but just plus the B value. So let me look up a average B value. These are much smaller, like 0.0426 is an example of one that might be close to what we'll find for sulfur hexafluoride, but it's again not SF6. So that should be our equation. And what did we say? Our volume should be slightly increased for the real gas because the particles themselves have real volume. The deviation will be less significant at low pressures and more significant at high pressures. So as we fill this down, we're going to start to see a huge difference in the volume, I would bet. Yeah, all right. Oh, wait a minute. Oh, okay, sorry. I was looking at the pressures. We want to compare these two columns right here. And we do see that in each case, this volume is larger than the ideal volume. Okay? So the last thing we want to do in this spreadsheet is the same thing that we did in column C, but now for the real values. We want to take equals real pressure times real volume divided by 0.08206 and 273. So that's going to be D2 times E2 divided by parentheses 0.08206 times 273. Okay. Again, this will probably be close to 1 at the lowest pressure that we have, closest to ideal behavior. But now here's where we're going to see in this ratio significant deviation from the moles of gas, all right, that we have. Okay. So you'll want to repeat this analysis that we've done here in Excel, and then to visualize this all. A picture is worth 1,000 words or 1,000 calculations in some cases. All right, we're going to make a graph, a plot, and so we're going to plot the two values that we have. So you actually have to make two graphs, but then you're going to make a graph, and this is similar to what's in your textbook of PV over RT versus pressures. So versus the real or the ideal pressures that you have over in that first column there. All right, and so the way you could do that would be to highlight the real pressures, click Control, and then highlight column C, P, down to there. All right, go to Insert a Scatter Graph, first choice. All right, and here is our graph. Now let me clear up the board so we can see this. Now this one doesn't change because these are all ones. Okay, click on one of these data points, right click on the mouse, and go to Select Data. All right, and we want to add a series of data. Okay, the X values, click this button for the X values. All right, and we can click the same ones that we had before. Oh, drag it down. Okay, and now dump it in with the arrow here. Okay, now the Y values we're going to want, click the button, are the real pressure volumes in column F now. So clicking F, dragging down to about 10. It looks like you got it. There you go. dump it back in. All right. And then, okay. Okay. We don't need to name it. All right. Something didn't go right. It made the graph incorrect. No, it did it.
They can put them vice versa.
They're vice versa in the first case, actually, aren't they? No, pressures. Okay, click on the red. Right click on the red. Okay, go to the data. Okay, this is series 2. All right, edit it. Okay, our x values are supposed to be the pressures. All right. So A's are okay, and our y values are supposed to be that. Should have these values here. I don't understand why it's not doing it. Okay, hit OK there for me. Let's see what it has for this one here. Edit. All right. X values, y values. That's really strange. C and F, those are the analogous columns versus A. These values should come out. Okay, hit OK there. Wait, let me see this right here. Again, series 2, edit. Change that 1 to a 2 right in here. Just type it right in there. Oh. No, you don't want the 1. I think you just want the numbers. There you go. It's gonna be all messed up. Okay, hit OK. Well, now hit the red button to go out. Hit the red button here to go out, and then just click again. Repeat hit delete, I guess, and then drag from 2 down to 10. Okay, and then do it here again. Now you gotta do 1, 2 down to 10 here. There we go. All right, now we can see it's fixed. Okay.
Yay.
All right. So this graph shows the deviation. It sort of visualizes this deviation for you, that as the pressure increases, and of course you would clean this up, maybe add some labels, change these labels here, okay? But you see that as the pressure increases, you start to get a larger and larger difference between ideal behavior, which is this nice steady line here, and real gas behavior. All right. So that's one of the take-home messages of this experiment. So you do that for sulfur hexafluoride with the gas that we're working with in lab, and then you repeat with a gas that you pick from your textbook. There's a table in your textbook in chapter 5 that lists the A and B parameters. Now, it gets so easy to do it for the other one. All you want to do, and we'll do this for him real quick, Lindsay, let's copy and paste this whole set of data right here. So we'll copy it. Now go down to a new sheet. Paste it. Paste it, okay? And it should have brought all of our formulas over with us. So the real stuff would be completely the same. All we have to do is go for our different real gas. All you have to do is go to that formula. This was your A value. You just need to change it and then fill down the formula. All right? And then change in the B value and fill down the formula. And everything will be updated. So it's not a ton of work to do this for all